Hey everybody, this is chapter 2. This chapter's a breeze, not really too much to worry about here. Let's get into it, eh? Section A is like super easy. Rational exponents. I mean, you should know this rule, right? So you should be able to write various expressions with radicals as exponents and vice versa. You should be able to see exponents and be able to think of them as various types of roots and whatnot. So hopefully this is straightforward and you don't need any explanations here. Section B, as a reminder, we have a few like shortcuts for expanding here as like a plus b times a minus b. That's a difference of two squares. This is going to give us a perfect square trinomial. Well, if you have expressions with exponents, you should think of them along the same lines. So in this first example here, we're just distributing x to the negative 1/2 into each of those, and so we're gonna add the exponents together because that's what you do when you multiply numbers with the same base but with different exponents. And then we get something like this in the end. Again, I hope you don't need too much explanation there. So here, in this first one, we just distribute like normal, and we get something like this. Okay, cool. In the second one here, oh, we got this thing that's being squared. Again, perfect square trinomial. So it's going to be 7x squared plus 2 times 7x times 7 to the negative x. Excuse me, I said 7x those times. 7 to the x. Plus 7 to the negative x squared. And so we get something like that. Wow, wonderful. We should also be able to factor various expressions with exponents. For each of these, it's nice to be able to, or rather, you got to be able to find a common term, right? So in this first one, we see 2 to the n here, so we want to pull out the 2 to the n from this part. Here we see 2 cubed is 8. Oh, okay, that's the common terms. Wonderful. Then here, yeah, this is 2 to the 3n, this is 2 to the 2n, and 2 to the 2n is actually the common factor there. Should be able to factor expressions like this as well. Notice this one here. This looks like a difference of two squares since we have 4 and a 9. And indeed it is, because 4 to the x is the same as 2 to the x squared. Right? And that's because they didn't really write it out this way, but 4 is, of course, 2 squared. So we can think of it as 2 squared to the x, which is the same thing as 2 to the x squared. Okay, and then same thing for this second one. We notice that, yeah, it says 9 to the x, but this 3 to the x, that's kind of a nice little clue there because we can rewrite 9 to the x as 3 to the x squared. And then we need to see this as a quadratic. This is something squared plus 4 times that same something plus 4, so we can factor that using what we know about quadratics. Please be on the lookout for things like this throughout the course, like secret quadratic expressions. Okay, next up, yeah, we can simplify stuff like this, right? So we know that when we divide expressions with exponents, we subtract the exponents, but that's only true if the base is the same. So here it's actually the exponent that's the same, not the base. So two ways that you can kind of think about it. I would do it this way over here on the right. I would pull the exponent out and rewrite that as 6 over 3 to the power of n, which is just 2 to the n. But you can think of it this way if you want to. 6 is the same thing as 2 times 3. So that's 2 to the n times 3 to the n, and then the 3 to the n just cancel. Whatever. Same idea over here on the right, just some different numbers. And here's some more complicated ones, but it's the same idea for all of them. We're trying to find, something in common with each of these terms. So in the first one, you see that you got 3 to the n showing up in those two terms. So like maybe we can get a 3 to the n out of that one. Same thing over here. We have 2 to the m in just by itself there. Oh yeah, we can get a 2 to the m out of that first term there. And then the one to the right is certainly a little more complicated, but after we take care of the factoring here, it turns out, oh, look at that. We get a 9 in the numerator, so that'll cancel with the 9 in the denominator. Very nice. Section C, finally getting a little more interesting now. So we've got exponential equations. Great, and we're going to do just easy exponential equations in this chapter because more complicated ones require logarithms. but we're not going to see logarithms until chapter 3. So for these, we're going to be able to just analyze the bases of both sides, and we should be able to work something out. So the idea is that if you can get the bases to both be the same, then that means that the exponents need to be the same. I think that stands to reason. So in this first example, we notice that 8 is the same thing as 2 cubed. So the equation can be written as 2 to the x equals 2 cubed, therefore x is equal to 3. That's super easy. Of course, it gets a little bit more complicated. Here's another super easy one, though. So 16 is the same thing as 2 to the power of 4, so that means x is equal to 4. Here we have to work for it at least a little bit more. 1 over 27, we recognize 27 is the power of 3. It's 3 cubed. So this is 1 over 3 cubed, which is the same thing as 3 to the negative 3. And once we're here, we have the two bases are the same, which means that the two exponents are the same, and we can solve. Here's two more. So in this case, there's no way that we're going to get 8, for example, to be a power of 4. However, both 4 and 8 are powers of 2. So sometimes we need to find the proper base, and it's not going to be one of the numbers that is immediately obvious to us. So 4 is the same as 2 squared. Okay, so that's the x, and on the right we have just 2 cubed. Multiplying those two together, we get 2x equals 3. That's easy to solve. And on the right, we'll rewrite both things as a power of 3. Again, 9 is 3 squared, so we have 2 times x minus 2. And that's all equal to 3 to the negative 1. So again, set the exponents equal, and we solve. Finishing up section C, we have yet another secret quadratic. All right, so again, look, 4 to the x, that's the same as 2 squared to the x, and that's the same as 2 to the x squared. So we have actually here a quadratic equation. And in this case, we could factor this one, so that ends up not being too hard. Otherwise, we could just use the quadratic formula or completing the square or whatever method you like. But we need to remember that we're solving here. Eventually, we're going to solve for x, right? So we from this step, we've got 2 to the x equals 4 or 2 to the x equals negative 5. This one's quite easy. Clearly, x is equal to 2. This one is impossible. 2 to the x could not possibly be equal to negative 5. You can't get a negative number out of a positive base. So we just have one answer. Okay, and then we get into thinking about graphs of exponential functions, which have, you know, basically it's going to have some sort of a horizontal asymptote, and then it's going to either generally go up in this first case, or it's going to go down. In both cases, away from the horizontal asymptote, or it's going to end up going down or going up towards that horizontal asymptote. So if our p-value here is positive, then we're going to have one of these two cases here, the two on top. And we call this one here exponential growth. We call this one exponential decay. It's either growing towards infinity or it's decaying towards its horizontal asymptote. You could think of this one as growth. I like to call this one negative growth because it's growing in the negative direction. And I call this one negative decay, although those are not particularly popular terms that you see out there. And just like we've seen in with function transformations previously, this h value here, it's next to the x, so that's going to control our graph moving left and right, and this k value is going to control our graph going up or down. Now we don't consider a coefficient of x acting as a horizontal stretch because, thinking about it in terms of, you know, like rules of exponents, if we had a coefficient of x, it could be incorporated into the base. It could be incorporated into the a. Like in the previous examples, when we saw like 4 to the x is the same as 2 to the 2x. Well, we would just consider that as 4 to the x. We would just make the base be 4. So, you know, I mean, you could think of it either way you want, but the book is just at least considering it as 1x. And I guess that simplifies matters a little bit, so we'll roll with that for now. Now we have a couple of restrictions up here. For example, a, our base of the of the exponent. It can't be equal to 1. Why not? Well, if this were 1 to some power, you know what? 1 to a power generally is equal to 1. So that's not really going to be exponential. It's just going to end up being some sort of a constant. We require also that a is a positive number. And that's because if we have a negative value here raised to a power, that's, things start to get a little wacky. If we raise it to an odd power, then it ends up being a negative number. If we raise it to an even power, it ends up being positive. If we raise it to a power that's not a whole number, we end up getting into a lot of trouble because we might end up trying to take like the square root of a negative or something like that. So when we talk about exponential functions, a is always going to be positive. And also p needs to be non-zero because if that were equal to 0, then this whole term would drop out. As always, grab some technology and play around with it, right? So we see the p-value, it's controlling the vertical stretch. It's not as obvious with this type of graph shape as it is with other functions, but as p gets larger, it is stretching vertically. As p gets smaller, it is being horizontally compressed. As soon as p gets less than 0, it flips over, so we have that vertical reflection happening there. The a value, that's just the base of our exponent, so I don't want you to necessarily think about that as having. It is related, as I mentioned a moment ago, with how we could, if we had a coefficient of x that's brought into the base. So technically, changing the a value is really affecting a horizontal stretch, if you want to think of it as anything. But we see, like I said, when a is equal to 1, it gets to be totally horizontal. And then when a gets smaller than 1, we end up having exponential decay rather than growth. And then when a is negative, just weird things happen. If you look really carefully, you can actually see some dots on the screen. And those are particular points where this function is defined, but there's all those gaps because it's really not defined for most values. And then we can play around with the h and the k. Those are just moving it around. So we should be able to sketch a graph by hand. Generally, like you want to just think about like the simplest version of it. So like if we consider f of x is equal to just 2 to the x, think about what that picture is going to look like. You know a bunch of powers of 2 already, so we should be able to work some stuff out. It's going to be exponential growth due to the fact that the p-value is 1 and then the a value is 2. We know that it's going to go through, when x is equal to 0, it goes through 0, comma 1, right? Because 2 to the power of 0 is 1. And then we know it's going to go through 1, comma 2, and then 2, comma 4. And over here we could have like negative 1, 1/2, and so on. So you kind of have a general sense of what the original graph should look like. And then we start applying some transformations to it. So we see that this is a negative x here. So that means that we're going to reflect over the y-axis. Okay, and then we're going to move down 3 units. And that's exactly what we see here. But again, there's different ways to think about it because we could incorporate that negative into the base and we could rewrite this as actually 1/2 to the power of x minus 3. And then we could think about what does the graph of y equals 1/2 to the x look like. And that's going to be exponential decay. And it's going to go like this. And it's going to go through, again, ignoring the minus 3 for just a moment, just 1/2 to the x. It's going to go through the point 0, 1. That's a popular point to be aware of when it comes to exponential functions. It's going to go through 1, comma 1/2. It's going to go through 2, comma 1/4. It's going to go through negative 1, comma 2. It's going to go through negative 2, comma 4. And we're just going to bring all of those down 3 units. And we get the exact same picture. So again, like identify which way does your brain like to think about this type of problem and just do it that way. Section E just has to do with like some word problems. So here the book officially discusses growth and decay, as I mentioned a moment ago. Really, there's not a lot of things in the physical world that have negative growth or negative decay. I'm sure we could come up with some examples, but most of what we're going to see is just standard exponential growth or exponential decay, like that. And growth populations is a very popular one for well, for growth, obviously, and then things like like half-life. So that's what they mean by radioactive substances here. Um, it's cooling down of hot objects, right? It's going to decrease, but it's not going to decrease forever. It's going to decrease to the ambient room temperature, so that should be exponential decay. They talk about items depreciating in value. So like when you buy a car, it depreciates to some particular flat value, but it's not going to decrease to zero or to like a negative number or something, right? Um, Another thing with exponential growth that they didn't mention here is like money in an investment, right? That's going to grow exponentially. So lots of examples that will use exponential functions to model them. So just here's a word problem for exponential growth, where we're measuring the area affected by a bunch of grasshoppers in this plague. This is classic. Love it. It's really not too bad though. Like they give you the model, they tell you what the variables stand for. Find the original affected area. Well, the original one was like when no time had passed. So that means we just set n equal to 0. That's pretty easy. It's just this number out here. Okay, that's cool. Letter B, find the affected area after this many weeks. We're just putting that into there and grabbing a calculator to, come up with some numbers, and we're rounding them, right, to 3 significant figures. That's all we got to do. Letter C, well, we're going to use a calculator for that, so we're going to draw the graph. Here it is. And we know like a few particular values. So like we've plotted the points here at 5 and 10 because that's what we came up with back in part B. And then part D, use your graph or technology to find out how long it'll take for the effective area to reach 8,000 hectares. So here we have kind of like an estimate from the graph, but I think we'd want to use a calculator for this probably. So we're going to graph it, and obviously nothing's going to show up on screen because my window is terrible. I want to see up until at least 8,000 on the y-axis. So I don't know, I'll do 9,000 in there. And well, they said that the x value should be around 14, I think. So I'll just take this out to 20. There we go. Oh, I forgot to give it my second value. We wanted to know when the area affected was equal to 8,000, I think. So there we go, and we're going to find out, menu, analyze the graph, where do they intersect? Amazing. So yeah, look, just estimating from the graph, it's like around 15. So if it were like a paper 1 type of thing, and you were like given this graph, then 15 would be a great estimate. Otherwise, 14.9 to 3 sig figs is better. And yes, you could also do this on the calculator using logarithms, but I'm not going to discuss that until chapter 3. Here's just another example that has to do with exponential decay instead of exponential growth. But I mean, it's the same thing. So I don't know, pause the video, read the question, think about it. Here's the answer. Okay, you should be able to do that without too much of a problem. So let's finish off this chapter here. We're going to go to section F now, which is about the best base for any exponential. It's called the natural exponential. It's the base of e. So, I mean, forget pi. Pi, boring number. E is where it's at. E is a wonderful number, and we're going to be working with it quite a bit this year. For right now, things to know about it, it's irrational, just like pi. It does have a physical meaning, which they mention here has to do with compound interest. But that's not the interesting part about E, I promise. So it's about 2.718. 28 are the next 2 digits. I don't have it memorized beyond there. E on the calculator is not accessed by pressing the E button down here. You could do e to the x and then type a 1 there, that's fine, I guess. But if you just press the pi button, it's in that same menu. Anyway, as far as we're concerned right now, e is just another number. It's somewhere in between 2 and 3, and we should be able to do all the other stuff from this video with e. So we should be able to factor exponential expressions that have an e in it. We should be able to sketch an exponential graph if it has e as the base, because we know that it's a positive number, somewhere between 2 and 3. Yeah, so there's really nothing else special to know about it right now, other than we should expect to be seeing quite a lot of it. Our textbook contains a little historical note on page 62 about the history of the number e. It was not originally discovered by this man here. However, he was the first to use the symbol e to describe this new constant. Now that man is Swiss mathematician Leonhard Euler. And I just want to emphasize the pronunciation of his name. It is Euler, not Euler. I know this is confusing to some people because we have this other famous mathematician named Euclid. This is coming from Greek, which I don't know how to pronounce Greek, but I assume it's something along the lines of how we say it in English, Euclid. However, this name is coming from German, so that is pronounced Euler. And Leonhard Euler is the greatest mathematician of all time. He was a leader in so many different fields of mathematics and stood so far above any of his peers and mathematicians to come for generations. I cannot overstate how influential he was to mathematics. And I don't mean to say that he was smarter than anyone who's ever come, in history. Certainly the top mathematicians today know more than Euler did, but that's because it was already figured out by him and by some others to make it easier for them to learn. Whereas he really discovered and proved so much. So Leonhard Euler is just a name that you need to know. And so today's concluding quotation is by Pierre-Simon Laplace, who is another famous mathematician who simply stated that Euler was, and when Laplace says our master, he refers to all of the other mathematicians and physicists in the world. Euler truly is our master in everything, and we will certainly be hearing more about him as we continue through the course.